Hello and good afternoon. My name's Jake Taylor. I'm presenting today as part of the ETSI Quantum Safe cryptography technical event. I'm based at the Joint Quantum Institute and the Joint Center for Quantum Information and Computer Science, partnerships between the National Institute of Standards and Technology and the University of Maryland in College Park. I'm also a fellow at the Belfer Center for Science and International Affairs at the Harvard Kennedy School of Government. Today I'm going to be talking about the United States perspective and preparations for the post-quantum world that awaits. I want to lead off today by describing the United States perspective regarding quantum science and what we're doing in this space. I encourage those of you who are interested in the United States' overall efforts and policies to go to quantum.gov, we'll talk more about that as we go, which hosts most of the strategic documents that I'll be talking about today. But let me highlight for those who are less aware the foundational document for the United States efforts in quantum information science today, which is the National Strategic Overview for Quantum Information Science. This dates back to September of 2018. It's one of the first documents that I helped put together in my stint at the White House. And in this, we identify the key policy directions for the United States to pursue to enable the quantum technologies that we hope to one day achieve. And one of the most important elements of this document you must understand is that for the United States, we see quantum information science as a science problem. And thus, we suggest focusing on a science-first approach. This is identifying and advancing quantum frontiers, the problems whose solutions are going to be transformative. To achieve even that, we also need to be increasing the workforce that we have, both in its breadth and depth. We need to have various mechanisms for industrial engagement and public-private partnership. We need the key infrastructure and support to realize those opportunities. And a substantial portion of this is developing in a collaborative manner to enable a large-scale positive change via quantum information technologies. And this is what I mean by creating a post-quantum world, a world where quantum technologies are ubiquitous and widely deployed, and where humanity can benefit. It's helpful to provide a small timeline for what we are doing and where we are in this space. And that timeline dates back obviously very early, but I'll start, say, in the 1980s with the advent of quantum key distribution, followed by the early 90s, the creation of the first algorithms for quantum computers, and 1995, the realization of the first 2-qubit quantum computer using an ion trap system at NIST in Boulder. Over time, the networking protocols here, italicized, and efforts have progressed on a sort of decadal basis, whereas quantum computing efforts have also progressed to the point where in the last year or two, we have seen 50-qubit controllable high-quality machines. And we're starting to see what I call engineering-grade qubits, qubits that have the capability of being engineerable. Projecting forward from where we are today, we're starting to get roadmaps from the large corporations working in this space, suggesting 1,000 or larger engineering-grade qubits before the end of the decade. We're also starting to see the advent of multi-party quantum computing through quantum networking protocols and the advent of nascent quantum internet protocols. And we're looking in the 2030s for high-fidelity medium-scale quantum computers, hi-fi MEC if you prefer. And then in the 2040 or so, we anticipate that initial quantum interneting protocols become feasible, and perhaps sometime that decade, larger scale, fault-tolerant quantum computing may see its heyday. This, of course, represents a cryptographic threat. And so, working backwards, it's important that by this point, here in 2030, that the classical cryptography and networking that we use to underpin our cybersecurity, our economic growth through internet technologies, be ready. And already back before 2010, I hosted one of the first workshops in what's called post-quantum cryptography at NIST. And In the middle of the previous decade, NIST embarked upon the standards setting process for cryptography standards that are going to be resistant to quantum attack. You'll hear more about the standards process in both Dustin Moody's talk and Lily Chen's talks, also as part of this ETSI event. And I encourage you to look to those talks for details on where we are in the standards process. But the goal is large-scale deployment around 2030, such that there is no doubt or fear or concern in the minds of all those who rely upon cryptography for their economic and social needs by the time large-scale quantum computers do become available. So many folks are thinking a lot about this space, but today I'm going to focus primarily up on here, which is the paths and steps that we're taking to get to these goals of a quantum internet and a large-scale fault-tolerant quantum computers, for it is non-trivial to do so. Within the US government, we have a large effort called the National Quantum Initiative. And this initiative drives forward and coordinates activities across more than 13 federal agencies. But the key thing you need to understand is there's three fundamental pillars of this effort. There's what's happening in the civilian space, what's happening in the defense space, and what's happening in the intelligence space. All of these represent efforts to ensure that the research is there, that we understand the science and the opportunities. But it's not just these research pillars, it's also the coordination, I'll talk more about that, and really enabling the emerging ecosystem and industrial efforts that can happen from this space. So we want to ensure that we get not just new defense capabilities, new intelligence capabilities, and new science, but also that we develop a new economy around the quantum technologies that emerge. This is done, of course, in conjunction with industry, with academia and other research laboratories, and with our international partners around the world. In terms of the coordination, for those who are interested, the National Quantum Initiative has a National Quantum Coordination Office. More details available at quantum.gov. This is an office that I created and led for the first year and a half of its existence, and located just adjacent to the White House. I left in this last summer and passed the torch to Dr. Charlie Tahan, who is available on Twitter at TahanTech if you want to reach out to him. The Coordination Office coordinates the activities across all of the different research agencies in the space. And I'll talk now about some of the results of this types of coordination. One of the things is, of course, creating new centers and new approaches for doing quantum information science to advance the science, as I've mentioned. And that means you really need to enable the innovation ecosystem. Now, I come from joint institutes. These are governmental academic institutes. And so we took some of the lessons learned from those joint institutes and applied them more broadly. That's looking at how you get physical co-location, dedicated infrastructure, long-term focus, and enable good talent flow and good information flow across the institute. Still, there's big challenges ahead of us, particularly around tech transfer and some of the challenges we have in realizing technology from science outcomes, interfaces with industrial and end user and manufacturer communities, and a broader sense of how we get skill transfer and training to happen. So rather than trying to solve this all at once, between the National Science Foundation and the Department of Energy, we put out a wide variety of calls for large centers and had different groups tell us how they could do this. These were funded this last year with the first round at the Department of Energy with their 5 centers and at the National Science Foundation with 3 centers. And there's another round of competition going on now. You can read about those details on quantum.gov or at the Department of Energy or National Science Foundation websites. We also need to get that industrial engagement in place. And towards that end, NIST has engaged with SRI International to create the Quantum Economic Development Consortium, which now has, I guess, around 160 companies that are involved in it. It is starting its international component as well. And the basic idea, you can read about it at quantumconsortium.org, is to provide de-risking of the technological pathways and supporting technologies and workforce around quantum technologies, so that some of the shared costs, concerns, and efforts don't have to be borne by any one company. And the thing you need to understand about consortia from the United States perspective is that consortia are really a government-backed pathway for cooperation and encouraging specific values for the participants. combined with information for the members and funding pathways. And the point of these is that it is trying to jumpstart the competitive market before the market exists. And that's ensuring that you cooperate at the right level, but that you also open up the competitive opportunities at the right time. Now, what's interesting from my perspective about the QEDC is not only its broad engagement and the many different members of the quantum industry that are involved, but the fact that it spans all companies all the way down to 1 or 2 person startups up to very large tech companies, and that the governance and participation structure supports that diversity of different industrial efforts. A third key challenge is the workforce. And one of the big problems here is that quantum information science and quantum computing, quantum networking represent disparate skills brought together, different needs and knowledge brought together. And it is rare within the academic structure that this fits perfectly well. Not only that, but it's complicated and technical, and people are often taken aback when they are told about quantum mechanics the first time. They're told it's not intuitive, they're told that it's challenging or difficult. And so one of our challenges here that we've been addressing has been getting an earlier education about quantum concepts. And towards that end, we launched the Q12 Partnership. This is a White House National Science Foundation, along with many members of industry and professional societies and teaching groups, in order to enable middle school and high school curricular development and courses, and to really codify and improve the core concepts. In fact, we have participated in a National Science Foundation workshop where we developed what are called the core concepts for quantum learners, which are the type of things that you'd like someone to know by the end of high school so that they can be ready to embark upon quantum information science learning in technical schools and community colleges and universities, and then soon afterwards, we hope, work in companies. But the point is, if you're a quantum company, your employee 10 years from now is in middle school. And so we have to get people in middle school and in high school excited, enthused, and moving, and use this as leverage opportunity to really enhance the fundamental mathematical foundation and science foundations that we have, in some respects similar to early aspects of the Apollo program. So let's now turn in the last tail end of the talk to what's happening in the networking space, because that's been a big change for the US federal government. And I should tell you, if we look at what's happening, we talk about quantum networking because, of course, there's quantum communication with quantum key distribution and many enabling technologies. But there's also the future of quantum communicating systems, and that's including quantum Internet of Things, where you have an internetworked set of quantum sensors, where the entanglement between the sensors enables new opportunities. There's also a key role for space-based systems to play. There's also what I call quantum squared cloud computing. That is a quantum computer hooked up through a quantum network to other quantum computers. That enables distributed quantum computing, interactive proofs, homomorphic computing, and much more. So we put together a strategic document outlining a vision in which the United States can help push forward these different aspects of networking, which is available on quantum.gov. And more recently, the quantum information science community in the federal government, through the Subcommittee on Quantum Information Science, which is coordinated by the National Quantum Coordination Office, put together a detailed research plan, which is available on quantum.gov, describing how to do this. And fundamentally, the point is you need to connect the research to early use cases to necessary infrastructure and ecosystem, which then enables the next round of research. Those are these increasing coordination, establishing timetables, and facilitating international cooperation. These are the sort of supporting elements to this. If we look at what we actually want to do, we need to support those research on the use cases of the networks. It's not just good enough to have the network, you need to know what you're going to do with it. You need to prioritize the core components, improve the classical capabilities for the supporting network infrastructure. So it's not just enough to have a quantum network, you need to actually have the network engineering that enables you to use that thing. And there has been some research in this, but it is not yet widely deployed or fully developed. And then we need networking test beds. So there's a lot of interesting things to come, and I'll just close by saying, if you look at what's happening in quantum networking, this is from the National Quantum Initiative annual report, you can see back in 2019 how we funded across supporting technology, sensing, computing, networking, and enabling and foundational science and technology. And if this is 0, you see that we were spending a lot on sensing, computing, and enabling, and not as much on supporting technology and networking. All of these have grown, but this has bumped out the most. So the US government is really starting to refocus in on quantum networking with the goal of realizing that vision of the future. Thank you so much for your time.